This paper is about multiplane image generation from a single picture. Novel view synthesis from a single view image is a challenging problem since it requires estimating the geometry of the scene and color textures for occluded regions. For this task, several representations could be used, for example, point clouds, meshes, layered depth images, and multiplane image. In our case, we are interested in the multiplane image representation, since it is relatively easy to generate and store, and needs a very simple rendering pipeline which does not require debuffering. However, MPI has some disadvantages. Since it's a voxelized representation, it can be very sparse. Also, for certain baselines, it may require several layers to result in a good visual effect. In this paper, we propose a new adaptive MPI representation. With our method, we not only estimate the visual content of each image layer, but also estimate the position of each layer, which is adapted to the input scene. We can also have a variable number of image layers depending on the input image without retraining our neural networks. Our method can be divided into three main components. First, given an input RGB image, we perform monocular depth estimation, which gives us an estimated dense depth map. The second stage is an adaptive MPI slicing step, on which we take as input the source RGB image and predicted depth map and compute a set of image layers in such a way that each image plane has some parts of the input image and is placed at a certain depth in the scene. Finally, the disocclusion regions in the image planes are inpainted by a neural network, so the rendered novel views do not expose holes during rendering. Okay. So now let's go deeper in our method. Monocular depth estimation is an ill-posed and very challenging problem. Even though recent approaches have demonstrated extraordinary results, they usually depend on complex training procedures with multiple datasets and very large CNN models. This can be prohibitive for some applications, especially if we want to deploy our models on device, like in a smartphone, for example. Considering this, our goal is to train a small size and fast CNN model, which should be capable of imitate a larger network. For this, we trained our lightweight CNN with internet pictures, using as pseudo-ground truth the predictions from a larger network. To improve robustness, our pseudo-ground truth depth maps were obtained using an ensemble of 10 predictions from Midas, and in different resolutions and with horizontal flip. Here are some examples from our dataset. We proposed a new lightweight CNN for depth estimation, which is small and much faster compared to Midas. The key ideas in our CNN are lightweight blocks inspired from MobileNet v3, intermediate depth supervisions, and wavelets decompositions for downscaling and upscaling feature maps. This results in fast predictions and sharp results, even for high-resolution images. The second component of our method is the MPI Slicing Algorithm. It needs to be fast even for high-resolution images and should avoid creating empty image layers. For this, we proposed a three-step approach. First, post-processing depth maps to reduce artifacts and reduce the smoothness of the borders. Then, we compute a normalized histogram, which describes a general depth distribution in the scene. The final result here is a slicing algorithm that cuts the scene on regions with higher depth discontinuities. In general, these regions are in the borders of valid pixels in the image layers. We want to extend the boundaries of these regions with generated color textures. For this, we defined the margin using morphological dilations. During training, we remove the pixels in the margin from the input image and supervise the network with the original image layer. During inference, the network expands the image layers, which avoids disocclusions. Now we can see some results. Depth maps generated by our method have better sharpness compared to a baseline without wavelets. When comparing our model with Midas, our network was able to surpass the teacher model on diode dataset, considering high-resolution predictions. It is important to notice that our light model is more than 14 times faster than Midas on CPU, considering high-resolution images. Now, we show some qualitative results from our method by simulating a camera movement. All input images are high-resolution pictures collected from the internet. Thanks for watching.